Welcome to the next episode of TORGiren DevOpses. Today we're going to continue our previous topic about files descriptors and look closer at the open function. We will go step by step through glibc and check out what open function do in user space. Let's start at the beginning and download the glibc sources. We're gonna find the newest. Yeah. Save, make directory, save, and okay, there we have sources and let's find out where is our open function. Let's try to grab open okay, maybe let's find our function open, and as we can see there isn't anywhere definition of function open, because there is some other function and open is just an alias. Let's find this one. Okay, IO no, sorry, sysdeps Unix sysv sysv Linux and open 64, because I'm going to show you the 64 bits the system. Okay. We can see that there is some weak alias from open to libc open 64. What is weak alias? Let's find this definition. It should be somewhere there, yeah. Libc symbols H, weak alias. Weak alias is defined as floor weak alias name, and this is one line below. It's a type of name, alias name, the attribute weak alias. So if we call function open, compiler knows that we want to exec libc open 64 function. Let's look for this function. So this is our main function, which is called when we do open, but it's not so simple. because there are 10 lines of code, but as we will see, there are many macros. So because there are many various defines, macros, and so on, I will do some trick which can help us to find out what this function do. Let's copy this function to new file. For example, DevOpses. Okay, this is a function glibc open 64, and now we will use some trick, because not everybody knows what GCC is. Most people think that GCC is a C compiler, but if we look at the main page, we can see that when you invoke GCC, it normally does preprocessing, compilation, assembly, and linking. GCC is just a collection of compilers and linkers. So if we invoke GCC, it will execute CPP, which is CP isn't a compiler for C++. CPP is the C preprocessor. Preprocessor operates on the preprocessor directives as such a include, defined, pragma, and so on. Next is CC, which is C compiler. There is also AS, which is GNU assembly, and LD, which is linker. But our trick will use CPP, because we want to dereference now, because we want to find out which defines we need and what they will do. So let's look at this is our function. Let's look at this macro, because it looks like a macro. Let's find out. Define. Is there a macro? Yeah. In file IO fcntl. Open this mode, okay. If def temp file, no, we don't use temp file. So if def temp file, this macro detect if open needs mode as a third argument, because as we remember, let's try this one more time. Open function takes first argument as path name, second as flags, and optionally third argument with mode. third argument is needed when we use create okay, this is some yeah. The mode argument specifies the file mode bits be applied when a new file is created. This argument must be supplied when create or a temp file is specified. So this macro finds out if our flags has attribute of create. So let's copy this one and include in our file. Okay, no, not yet. So our C preprocessor, and let's preprocess our file. We can see that this is our file. Nothing was changed because we have none of preprocessor directives. Now we know that open needs mode is a macro. So let's add this macro, define open needs mode, and preprocess our file now. We can see that need flags was changed to O flags and byte end with create. This code check out that if in our flags is set create bit. How it works? It's byte operand. So if our flags has I don't know, some bits set up, and our create variable has only one bit set. For example, this one, then the operation end will result in 0 because 0 and 0 is 0, 0, 0, 0. Here is also 0, and we have all zeros. But if our flags are for in this form, this position will be 1 because 1 and 1 in bit logic is 1. So let's back to our file. We can see that we are checking that result of this operation is different from 0. So this is easy way to find out that create flag bit was set up. If yes, we do some operation. In this example, we read the optional variables from function code. Okay, so this one was quite easy. Now we have syscall cancel, which also looks like macro. So let's find where is defined syslog cancel. In sysdep's Unix sysdep h syscall cancel, and we can see that this isn't a simple one-liner, so maybe we can open our file and just copy that macro. Okay, let's open another terminal because we need somewhere to cdp DevOps. Okay, as we can see, our function with return syscall cancel was replaced by so much code. Okay, maybe we can try to set something. Okay, we can see that there is return bracket and block code. Here we create long int variable, and we have some if single thread p. Let's find out what does it mean, but I think this is information that we have. Okay, sysdep generic sysdep cancel. I think this is okay, so let's add this to our no, not this one to our file, and if 1, so this is always true, scret is equal to inline syscall call. So this is also some macro which is defined as was inline syscall call. Okay, this is this macro, so let's copy this one, and we can see that inline syscall call will use inline syscall disp, so we can find this macro here and copy this one too. As we can see, this one use syscall concat. So let's find out where is syscall concat. Nice. Okay. As you can see, it will use syscall concat x. So let's copy this one too. There is so many macros in glibc, so let's try it now. As you can see, there is inline syscall and args, some arguments, maybe another macro, this is else, which I think isn't important in our example, because we will take the simplest way to call a syscall. So I think this if is good enough. So let's look at the inline syscall and args. Yeah, it's here. It will use inline syscall and x, and this code do one simple thing. Let's take a look. We have inline syscall and inline syscall and args, and we provide 1, 2, 3, 4, 5 arguments. When first is syscall name and 4 arguments. Now we can pre-process our file, and our inline syscall and args was replaced by 4 because there were 4 arguments. Let's take a look. So look at these two macros. If we call inline syscall and args with, for example, okay, let's maybe copy this one because it's quite interesting. Okay, it's two macros. If we call inline syscall and args syscall name and arg1 arg2, it will be replaced by this line. So our VA args are syscall name, arg1, arg2, and 7654321 Now this macro is replaced by n. So our A value is syscall name, our B value is arg1, our C value is arg2, our D value is 7, E value is 6, F value is 5, G value is 3, H value, no, I missed something. One more time. Maybe I will copy this line. Okay, this is syscall, syscall name, arg1, arg2, 7, 6, 5, 4, 3, 2, and all of it is replaced by 2. If we have arg3, then A is syscall, arg1, arg2, arg3, 7, 6, 5, 4, 3. So if we have more arguments, the higher number will be at the end position. If we have arg4, arg5, arg6, arg7, then our A is still syscall, arg b is arg1, arg2, arg3, arg4, arg5, arg6, arg7, and here goes numbers, so n is 7. It's quite interesting method to find out how many arguments we provide, but it's interesting but not so simple at the first view. Okay, let's continue. Here is our function. We have new macro, which is built with from two other macros. So let's find this macro in our file. Yeah. Define inline syscall 4 because we have 4 arguments. Okay, 4 because 3 are our arguments: file, open flag, and mode, and one extra argument is something hard-coded at fdcvd, cwd, but it will be later. Okay, inline syscall 4. We have to copy this one, and we can see that it will use inline syscall. So let's find inline syscall. We have here macro inline syscall, but let's check out there isn't another more specific, because it's quite general file, and sometimes there are more specific macros. So let's find, is there anything anywhere? Yeah. As you can see, many of architectures has own implementations of inline syscall. We will look at our 64-bit inline syscall. Yeah, there is some definition, but as you can see, there is else. We have to find out what this if means, because maybe it's nothing important. So let's find out where this defined assembler. Okay. So there is some value assembler, so, and it's important how we call our Cisco. So let's find out what this variable is, and we can see that sysfile linux test signal numbers is h. Okay, I can't find anywhere definition of assembler. I don't know what this variable macro is, so let's go through non-assembler way. Yeah, else, not assembler, and we use this Inline Cisco macro. So let's copy this one, and we can back to our pre-processing. So our function will now return a signal assigned long int result var internal Cisco. Internal Cisco is defined it's also a architecture specific, so we have to find out our 64 bytes, and okay. Internal Cisco, what? Okay, now here. Yeah, it's our file, and here we go with internal Cisco, which will call internal Cisco with number from the arguments. So we have to find Cisco number, and it's not here, but no, it can be here. Okay, so let's pre-process, and we can see that our syscall has 4 arguments, so we need to internal syscall 4 macro, and it should be somewhere here. Internal syscall macro 4, yes. Let's copy this one, paste, and pre-process. Okay, now we can see that our code is almost done. We have few more macros, type phi and arg phi. We can find them. Okay, so type phi is here. No, define. Well, it's here. There are 2 small macros. We will copy them as well. Okay, and as you can see, our type phi make type of, and our arg phi also type of argument. So this one should be compiler options. Now we have extra open flags. And as you can see, there are only in Linux. And let's check out extra open flags. If dev I don't know which one, what does it flag do, so Let's find out. Maybe there is some documentation about this flag. No, there isn't. Okay, we can see that this flag is defined in 32 bits, and okay, so we go the way without this flag. If def we can meet this value. Let's use this value. It's not important in our example what exactly value it will be. Okay, extra open flags. No, I'm not here. Here, yeah. Let's pre-process one more time, and as you can see, there are no more macros. I think it's some constant. Okay, and the last one, minus 100, yeah. And we've got our function which create a variable. If true, set scret another variable which is another variable, and there are variables that will hold our arguments, mode, flags, file, and some constant. Okay, we have one more macro, specify. Let's find our architecture. Is that maybe I have opened this one? Okay. Okay. It will replace syscall name with number of this syscall. Because here we I just replace that, but we had something like, I can't find it now. Yeah, here. We provide our syscall number, but there is still a macro with name of syscall with sysif. We change this to some another macro, and let's look for this one, and this can be problem because there can be, there is no such value, because if we look for it in my sources, we can see that this value is in generated. So this syscall values are generated in compile time, or maybe in compile time. So we have to copy this one from my own sources. It's kernel sources. Not glibc, and so let's copy this one, and it's our last preprocess, because now we can see we have one more thing. We can see that for our architecture, this okay, it's done. So let's look at our code. One variable, another variable, no, it's the same, another variable, another, and this is important because here we create 4 arguments, one for mode, one for offlags, one with file, and one with some constant. Which one of these args has type of itself? So here we it's the simplest example. So -100 is integer, so -100 is integer, type of integer is integer, so this argument will have type integer, and value which is assigned is also integer and -100. The same goes through for all of 4 arguments. Next, we create 4 more arguments, variables, A4, A3, A2, A1, and we have register before definition. This one tells a compiler to put this variable into register. Let's look at the example. Let's write a simple application. Main, and let's create variable x with value 4, return 0. Let's compile this one and decompile. We can see that we move value 4 into heap where the place for our variable is. If we create y and z, we can see that all of these three variables are stored in heap. Okay, but what if we add register before our definition? We can see that where is our 5. Okay, as you can see, there is our move 5 to some register, and what the next line is create our a variable, because a is equal y. Yeah. Okay. Move 4 to heap, move 5 to register, move 5 from register to heap, and move 6 to heap. Okay. This is very useful in loops because register variables are very quick. So we create 4 variables and store their values in registers, but here is another attribute with register name. So let's look how it works in our small example. Like this. Looks like this one. Okay. We can see that our 4 goes to ABX and our 5 goes to R12D. Some random registers. But what if we want to put this variable to AX and this one to, for example, R10? Ouch. This is another macro. No, my bad, I think, yeah. should be here and here. As we can see, we put 4 in AAX and 5 to R10. Okay, so the same thing is here, because we want to put mode into R10, offlags in RDX, 5 in RSI, minus 100 into RDI. Why? Because there is something called AB. Okay, calling conventions and I don't know is okay. Yeah, we have. There is some nice table with system V and the 64 AB and parameters in registers, RDI, RSI, RDX, RCX, R8, R8, R9. Maybe there is some. It's the same here. If we call syscall using system V AMD 64 AB, we have to put our arguments in specific register in specific order. So first argument goes to RDI, RSI, RDX. R10 is used for as a static chain pointer in case stuff. So, and we should put our syscall number in RRX. Never mind. So we put our arguments in RDI, RSI, RDX, R10 registers, and then we call syscall. So we have this assembler call. Let's find out how it works writing some application, and we will use their three variables, and we need result var. So this there's something strange about this line. Maybe it was, yeah, okay. Okay, so it's pure assembler call from C application, it has following syntax. Assembler code to execute. In our example, it's syscall. Output. We want to get our output to result var. Okay, and after colon we have input. Our inputs are these four values, and this tell a compiler which registers and places can change through this call. So let's compile and replace them. Okay, let's use X one more time. Okay, I don't know why, but I can't use 0 here. But we need to okay. I know why. Because we need this one to be in EAX, okay, and our X element is already in this argument. So now this should work. Yeah, let's look at our example. We create 3 variables in registers and use syscall with these parameters. So compile, object dump, and we can see that our value 4 okay. Our value 4 goes to the E, our value 5 goes to R10, and our value 6 go to R11. And there is our syscall, because this is our assembly code. And when we back to our open function, we can see that there is that one assembly code, syscall, and from this point further steps to open the file will be in the kernel space, but this will be in next video. This has 1 hour, so it's too long to make everything in one video. Okay, thanks.